Okay, hopefully this is welcome back for you. This is part 2 of our Chapter 1 Mechanics. And these are the topics that we just have to, we can't afford to be pretty good at these. We have to just nail these. So we're going to start off on number 49, right where we left off from the previous video. And this is factoring and factoring quadratics. You should be familiar with the Hananiga method for factoring quadratics, but we're going to review that. And in this quadratic, again, the first thing we want to do is we want to look and see, can we divide out a monomial from each term? And we cannot. Then we want to take this 1 times this 12. I get positive 12. I need two numbers that multiply to be positive 12 and add up to be positive 8. And sometimes it's a big search, but when it's just positive 12, there aren't too many choices. 1 and 12. 2 and 6, 3 and 4, but 2 and 6 get it done. But positive means the signs have to be plus and plus, 2 and 6, and typically we would put these over 1 or over the coefficient in front of the squared term, but of course those stay the same, and our result is a plus 2 times a plus 6 are our factors. We're not solving this. There is no equal to. I don't want to see a equals negative 2 and a equals negative 6. This is just meant to be factoring. So those are our factors. Can't stress this enough. At this point, if you're a little bit uncertain, you can go through the foiling process. And in the foiling process, we would get an a squared. We would get 6 a's and 2 more a's for 8 a's. And we would get a positive 12. It only takes a few seconds to check the foiling process. Okay, let's take a look at one maybe a little bit more involved. And the obviously most common mistake made on here is we just start saying, okay, I need two numbers that multiply to be whatever 4 times negative 96 is. But before we start, we want to try to divide out any monomial. And clearly at least 2 divides each of these, and maybe 4 does. So it's 4 times x squared plus 2x. Negative 96 divided by 4 is negative 24. So we've got past the first common mistake. The next common mistake is to forget about this 4 down the road. I'm not going to. I'm going to put a box around that so and know that thing's going to get carried along later on. So now I'm just looking for two numbers that multiply to be negative 24. Well, if they multiply to be negative 24, one's positive, one's negative. And they add up to be positive 2. So the positive number is stronger. Again, 24, not too bad, a little worse than 12 in the previous problem, but factors of 24 that fight, positive and a negative, to be 2 or subtract to be 2. 1 and 24, that's 23. 2 and 12 fight to be 10. 3 and 8 fight to be 5. 4 and 6 fight to be 2. So if 6 is positive and 4 is negative, we've got two numbers that multiply to be negative 24, add up to be positive 2. So because this is a 1, I don't have to simplify anything. My final factors include a 4, wasn't going to forget that, and an x plus 6 and an x minus 4. Okay, number 53, it's a binomial. There's only 2 ways we can factor binomials, and that's to undistribute or factor out the GCF and or to hope that it's difference of perfect squares. So 24 and 120, clearly I can get something out of that. I can get a 2, I can get a 4. I can even get a 24 out of here if I look long enough. So I'm going to factor out a 24. Both of these terms have at least a p to give. And now I'm just undistributing it. I undistributed a 24p. So 24p times another p would give me 24p squared. And 24p plus times minus would give me a minus. 24 times 5 gives me 120, and I don't need another p. And then I see I can't factor anything out of the p minus 5, at which point I'm done. Okay, know you've had lots of practice on factoring, and we'll probably get quite a bit more. Here's one more problem. The first thing I'm going to do is look and see, well, 6 and 19, I can't factor anything out of 6 and 19, and all three terms don't have a v, so this is a little bit more complicated factoring. I need two numbers that multiply to be 6 times negative 20 is negative 120. They need to add up to be positive 19. Since they multiply to be a negative, one's positive, one's negative, therefore the factors are fighting or subtracting to be 19. Well, when the numbers are bigger, I like to do this. How did I get to 120? I got to 120 with a 20 and a 6. And 20 and 6 fight to be 14. So I always just adjust the small number. 14 is not too far for 19, so if there's magic numbers, they're close to 6 and something. So which direction do we go? You could just randomly choose to try 7, try 8, try 9, or try 5, try 4. But if the numbers fight, we subtract. These numbers are 14 apart. I need my numbers to be farther apart. I don't want to try numbers between 6 and 20. I want to get farther apart. So I might try 5. And 5 goes into 20 24 times, and those fight to be 19. So I've got my magic numbers. So 24, excuse me, must be the positive. 5 must be the negative. Next step, I put those numbers on 6. And I have to reduce these for this to work. Well, 24 on 6 is plain old 4. Negative 5, 6 does not reduce. So what I refer to as the prefactors would be v plus 4 and v minus 5, 6. But that really doesn't work, because if I FOIL this, I get v squared. I don't want v squared, I want 6v squared. So if I put a 6 out in front of here, I would get v squared times 6, and hopefully everything else would work. Well, if I take this 6, again, I talked about this on the first video. Let's say I had 6 times 2 times 3. We all know that's 1236. But I don't take, even with parentheses here, I don't take 6 times 2, 12, times 6 times 3, 18. That would certainly not be 36. I just multiply 6 times either one of these two first. I'm going to choose to multiply 6 times this factor. So I get v plus 4. When I distribute 6 into here, I get 6v minus 5. And you can kind of see we could do this just by taking this 6, putting it in front of here. Let's take a quick FOIL test here. V times 6v, 6v squared. V's, I get minus 5v's and plus 24v's, 19v's, and I get a minus 5. And we're good. We call this step, where I put the 6 out in front of here, smithing it. And I can explain that in class if anyone wants to ask a question on where the origins of smithing it came from. So that is our more complicated factoring. When you get on to problem number 56, looks terrible, factors 12 and 84, but I wouldn't be surprised if you can take a common factor out of those and reduce those numbers a little bit. Okay, sketching graphs. Now, probably the best way to sketch graphs is to go ahead and solve for y, get slope-intercept. However, when they're in standard form, it's at least worth taking a look at this. What if we look at when x is 0 and y is 0? When x is 0, I get 2y equals 6, 3. When y is 0, I get 3x equals 6, 2. And I've got my points. That's not always convenient, as you'll see shortly here, but when they're nice integer values, 0, 3, 2, 0, let's get a couple more points on. We've established our slope, down 3 over 2, down 3 over 2, down 3 over 2. I like to get as many points as fit on there, or up 3, left 2. Let's see here. Something for a straight edge. We'll just use this. It's not quite straight, but pretty straight. Take some pride in your lines. So we have that. Now, when they're in standard form, is that always convenient? Well, let's see. If x is 0, y is 5, I can see that quickly. When y is 0, I'm not so crazy about that one because I don't want to work with fractions. So we could take this equation, 7x minus 4y equals negative 20, and solve that for y. I'm going to subtract 7x. I get negative 4y equals negative 7x joins a minus 20. Divide negative 4 to get y alone. I get y equals positive 7/4 does not reduce x. Minus divided by minus plus, 20 divided by 4, 5. And one of the important things that I want to really emphasize is since this is positive, my line is either going up and to the right or down and to the left. It's either up right or down left. I have a positive slope, so I start up at 5. Y-intercept 5. I'd like to go up 7, right 4. I don't have room to do that, but I do have room to go down 5, 6, 7, left 4. Notice my line is still going up as we move to the right. So we end up with this line. So there's two different ways of handling graphing lines when you get standard form. This looks 58 looks like it might be a good one to do with the x equals 0, y equals 0. But for 60, I might be more tempted just to solve for y. You can do it either way, either problem. Okay, more inequality work. To be honest, this inequality work should be a little bit easier than the absolute value inequalities we did earlier. Okay, so I want to get r alone. I'm going to subtract 1. I get negative 96. When I subtract, greater than signs stay the same, is greater than negative 6 times 1 plus 5r. Now, I could distribute negative 6, or if it conveniently divided out, I might divide it out as well. We got some options here. I'm going to divide out negative 6 here. When I rescue a negative, and this is discussed on the previous video as well, when I divide an inequality both sides by a negative, greater than signs change to less than. So I end up with positive 16 is less than 1 plus 5r. Well, from here, subtract 1. 15 is less than 5r. Divide 5, and I get 3 is less than r, but I would prefer to know what r is, not 3 is. This says 3 is less than r. Therefore, r is greater than 3. If r is greater than 3, r can't touch 3, so I build a little force field around 3. But if my numbers are bigger than 3, they are part of my solution. So bigger than 3 is out this way. Nothing to it. Things we have to be careful with there, just managing greater thans. When do they stay less than, or when do they become less than? When do they stay the same? Number 63, first step. Add 6. And again, you could distribute and combine and do things like that as well. You could certainly work to simplify the entire right side. I'm going to add 6 to both sides. I get 108 is less than. Let's just handle this one a little bit differently, just so you see it doesn't really matter. I'm going to go ahead and distribute here. 16b minus, plus times minus minus, 4 times 1, 4. On a side note, one thing we could not do that I see happening occasionally is I see people take -6 plus 4, make this -2. I can't do that because now the -6 is kind of being a part of what gets distributed in here. This multiplication has to be done before we combine the -6. Okay, add 4. Add 4. I get 112 is less than 16b. Divide 16, and I get 7 is less than b, but I would rather see b is greater than 7. Therefore, 7 cannot be touched, almost can be, and we're okay if we are bigger than. B is greater than 7. Okay, similarly, compound inequalities. Compound inequalities. I could break this into two separate inequalities. I could say -89 is less than 1 minus 10x, and then also say 1 minus 10x is less than 11 and solve those separately. But if they're written this way, compound, I can just do this all in one step. I just have to do the same thing in solving for x. I just have to do the same thing to each 3 partitions. And the first thing I would do is subtract 1, subtract 1, subtract 1. So I get -90 is less than -10x is less than 11 minus 1, 10. And then careful. The next thing I'm going to do is rescue a negative using division. Does that have a familiar ring to it? If we rescue a negative using multiplication or division, the signs change. So I get +9 is greater than x is greater than -1. Let's take a look on our number line. I want a 9, and I want it circled. And I want x's, I want 9 to be bigger than my x's, or if I read it backwards, x's to be smaller than my 9. That way. I want a -1. I want it circled. And I want x's that are bigger. So I want values that are in between. This is an and problem. The answer could look like this. It could also be, let's flip everything, -1 is less than x, just looking at it backwards, is less than 9. Or it could be x is greater than -1 and x is less than 9. And I could live with any of those, but you need to be aware that it could be any of those types of answers for a multiple choice question. Okay. Here's another compound statement, but however it's written differently. Here we have an and in the middle. We have 2 separate problems to work on. On this one, I'm going to rescue 9 with addition. 6x. When I add to both sides, greater than, stay greater than. Negatives mixed with positives fight. This is +48. Rescue +6 with division. When I rescue positives with divisions, greater thans stay greater than. So I've got a mistake here. This is -48. So at -8, I need a solid dot I can touch, and I'm just going to give myself an arrow. I want x's that are bigger than. Let's take a look at the second equation. Add 2. I get -5x stays greater than 25. I am now rescuing a negative using division. I'm very conscious of that because I know that's a common mistake I've made in the past. Signs change. X is less than 25 divided by -5, -5. So -5 gets a circle. Well, -5 would be here, and I want x's that are smaller than this way. There's my number line solution. Numbers are in the middle, as explained on the previous video, makes this an and problem. But we fully expected that. Okay, now ultimately you could just enter this excuse me, exactly as it appears in your calculator and go from there. But For right now, we're going to go ahead and show this work. I want to work inside of parentheses, so I can work this one, 9 minus 5, 4, divided by. I'm going to work this one, so these parentheses are still alive and well. 5 minus 2, 3. 3 minus 1, 2. Plus 5. I've still got parentheses alive. 4 divided by 2 plus 5. Division before addition. Please excuse my dear Aunt Sally. Parentheses exponents. Multiplication, division. Addition, subtraction. So I get 2 plus 5 or 7. Hopefully we don't have challenges there. So 71, I want to do parentheses first. And I know we could maybe do this division first, but I'm going to come back and talk about that. 8 divided by 4 times, in parentheses, 3 minus 3, 0. 0 plus 6, 6. Times 15 divided by 3. So please excuse my dear Aunt Sally. I'm going to write this without the parentheses. Please excuse my dear Aunt Sally tells us we look for parentheses first, then we look for addition, so please, then we look for exponents, then we look for multiplication, division, addition, subtraction. But where some people get confused on this, and I understand why, multiplication and division are together, addition and subtraction together. Multiplication does not have preference over division. Addition does not have preference over subtraction. We just go left to right. So left to right, I get 2. Now, can we get away with multiplying 6 times 15? Can we get away with dividing 15 by 3? Better be careful with that. 2 times 6 times 15 divided by 3. Left to right, that's 12 times 15 divided by 3. That's 12 times 15. That would be 150 and 30. That's 180 divided by 3, or 60. Again, I'd expect probably we might just, even though the numbers are pretty easy, we might just go to calculator here. Okay, first thing we would do here is look for we find no parentheses, but we got an exponent. But we could also do this division in that step. So 1 plus 2, 2 squared, plus 4, plus 3, plus 3, and then I would expect at this level we're all just going to do that one in our head, and maybe we all do it in our head beforehand. We get what? 3, 7, 10, 13. Nothing to it. Okay, I suspect when you get to percent problems, you have seen things like this. That if I take 37 is means equals, what percent, I'm going to call that P, and of is times 149. And then we solve for P and we turn that into a percent. The way I've always taught this for first time is with this. And you can do it this way, but I've always taught it as is over of equals percent over 100. So every single problem like this I would do with this little rubber stamp. Something over something equals something over 100. And then I just put the parts in place. Once again, it's like puzzle pieces. 37 is only with an is. 37 is here. What percent of? Now, what percent? I'm going to call that P. What percent is with is on one side and of on the other? But it can't be the is. 37 is the is. So what percent is over of equals percent over 100. 149 must be my of. Is over of 149. And now, if we cross multiply those, we get 149p equals 3,700. Divide by 149, and I'm going to go to calculator on this guy. I get 3,700 divided by 149, or P is approximately, if I go to the hundredths place, 24.83%. So I really like is over of equals percent over 100. If you want to just set them straight up in an equation, that's fine. Notice when you took the 37 divided by 149 up here, you would still have to convert that from 0.2483 into 24.83. I'm a big fan of is over of equals percent over 100. That has worked at all different levels with students. So let's just handle these that way. Is over of equals percent over 100. Something over something equals something over 100. And I look, 57 is clearly my percent. By the way, per cent, per, divided by cent, 100 cents in a dollar. Percent divided by 100. Okay, so what is 1.6? Is it the of? Is it the is? Well, what? I'm just going to call that n or x. I wouldn't call it p because my percent's already taken, so I'm just going to call it n. N is clearly the is, so is. Now that makes no doubt. If n is the is, 1.6 is the of. Is over of 1.6. So I get 100n equals 1.6 times 57, 91.2, divide 100, and we get n equals 0.912. Is that a percent? No, my percent was already discussed. Okay. Number 79. Is over of equals percent over 100. That's my rubber stamp. I start every problem like that. 70 has to be the is. What percent? That must be the percent. I'm going to call that p, just to remind myself to put a percent sign. 160 must be the of. Cross multiply. 160p equals 70 times 100. That's a 7 with 3 zeros. So P equals 7,000 over 160. 7,000 divided by 160 is 43.5. Since it's a P, I'm not quite done. Need a percent sign. So I'd really encourage you to try is over of equals percent over 100. Okay. As it stands, combining these, this is kind of like having 2a minus 3b plus 3c. I can't combine. I couldn't simplify this expression. However, if I can make any of these radicals be the same, like let's say I could make this 2a minus 3a, then I can combine the 2a and 3a. So what I'd like to do is simplify the radicals. And to do that, I call it jailbreaking. In other words, I want to find 6. Are there any perfect squares that divide into 6? Well, only thing that divides into 6, 1, 2, 3, and 6, none of those are perfect squares. Or if I factored 6 down, I'd just get a 2 and a 3. But what I'm looking for inside of these radicals are pairs of factors that match. And I use factor pyramid, and I'm going to do it this way. I'm going to start with, we don't need to see that. I'm going to start with 54, and I'm going to divide in prime numbers into that. So I want to take my smallest prime numbers that will divide into that. I'm going to start with 2, and I'm going to use 2 until it doesn't work. 2 goes in 27 times, and I'd try 2 again, but it doesn't go. So my next prime number is 3. 3 goes in 9 times, and 3 goes in again 3 times. And 3 does not factor down, so I get this little hockey stick. So this could be written as 2 times square root of, instead of 54, 2 times 3 times 3 times 3, but I want to put those in pairs if I can. So that's 2 times a pair of 3's times another 3. If I can get a pair like that, I call it jailbreak. So I say if you're in the radical, you're in jail, but if you've got a 2 as an exponent, you can bribe the guard to get out. So this 3 can pay the guard 2 and come out and join, I call this my getaway driver. I've got 2 times this 3 bribes his way out of jail, but leaves behind the 2 times 3. Or I get 6 root 6's minus 3 root 6 plus 3 root 3. And now I've got 6 apples minus 3 apples. 6 apples minus 3 apples is 3 apples. 6 can't jailbreak, 3 can't jailbreak. All right, let's take a look at another one of those. This 3 cannot be jailbroken. 45 maybe. Let's try it. 45 factor pyramid. 2 does not go in, but 3 goes in 15 times. 3 goes in again 5 times. So I have negative 2 root 3 minus, these 3's could bribe their way out of jail, leave behind a root 5. Do we follow that? I'm going to factor pyramid 27. 27. 2 doesn't go in there, but 3 does. 3 goes in there 9 times. 3 goes in there 3 times. Therefore, these 3's can break their way out. Join the 2. 2 times 3 is 6. Leave behind a 3. I've got negative 2 apples minus 6 apples for a total of minus 8 apples minus 3 root 5. And those can't combine. Once again, and I should say this more often, if you feel like you can do a problem, you might want to pause the video and do it. There's a chance maybe all of these jailbreak a little bit, and we have to simplify this. So let's start with the 45. 3 goes in 15 times. 3 goes in 5 times. So on that hockey stick, I got a pair of 3's. Join my getaway driver. Negative 2 times 3, negative 6. But 5 is stuck in jail. Same, minus 3 times my escaping 3 here. Minus 9. Root 5. How about 12? 2 goes in 6 times, 2 goes in 3 times. 2's can break out of jail. Join this 2, minus 4, leave behind a root 3. Combine what we can combine. I've got apples and oranges. Negative 6 apples minus 9 apples minus 15 apples and minus 4 root 3. Can't combine those. Okay. Number of problems like this, last page on here. When we get radicals mixed in fractions, the first thing we should always do is try to make the numbers smaller. And any numbers we can make smaller, there's 3 ways we can do it. And one is to reduce as fractions. And I can reduce plain old 4 and plain old 2 to become plain old 2 and plain old 1. And I can reduce square roots as though they're fractions. 16/12 reduces by 4 to 4 and 3. So the first thing we do is we reduce as fractions. I'm going to come back to that problem. If I was going to reduce this problem as fractions, I'm stuck with a plain old 3 in the top, but 10 and 15 reduced by 5, so I get root 2 and root 3. If I was going to reduce by fractions, 5/4 doesn't reduce. Root 5, root 2 doesn't reduce. Okay. The next thing I like to do is I like to see what I call a V8 moment. And a V8 moment would be if I was factor treeing, let's say I was factor treeing 36, or factor pyramiding that. I take 2 in, it goes in 18 times, and I take 2 in again, and it goes in 9 times, and I take 3 in, and it goes in 3 times, and I'd get square root of a pair of 2's and a pair of 3's, so 2 escapes jail, 3 escapes jail, and I get 6, and I'm like, oh my gosh, square root of 36, I knew that was 6. If you've seen the V8 commercials, it's like, wow, I could have had a V8, and that's when the guy kind of thumps himself on the head as he says it. Holy smokes, I made a mistake. I could have had a V8. So my V8 moment happens right here. Square root of 4 is 2. I get 2 times 2 over plain old square root of 3, or 4 root 3. Now, to be considered simplified, I can't have radicals in the denominators, and I'll explain that in class why we don't want to have radicals in the denominators. So what I've got is my jail situation. How could this root 3 get out of jail? We'd need another root 3 down there. But I can't just go multiplying denominators by root 3, but if I multiply by root 3 over root 3, I just multiplied by 1. So I didn't change the value, just the form. And I get 4 times square root of 3 over square root of 3 times square root of 3, 3. Can I reduce this 3 with this 3? No, this is a square root of 3. Can I jailbreak the 3? Jailbreaking actually is my third way of making numbers smaller. I can't jailbreak 3. So we reduce the fractions, or we reduce the numbers 3 ways. 1, we look to see if we can reduce as fractions. 2, we look for perfect squares, or the V8 moment. And 3, let's say I reduce the fractions, and in the denominator I got a square root of 24. I jailbreak that. Okay. This problem, do I have a V8 moment? No. Square root of 2, I don't know exactly what it is. Square root of 3, it's not a nice number. Can I jailbreak 2? No. Can I jailbreak 3? No. So I rationalize by giving this 3 a partner to break out of jail with. So I get 3 times root 2 times root 3, root 6, square root of 3 times square root of 3, 3. Can I reduce this 3 and this 6? No, it's a square root of 6. Can I reduce this 3 and 3? Yes, they're plain old numbers. Okay. Number 91. Can I reduce the 5/4? No. Can I reduce the root 5 on 2? No. Do I have a V8 moment? Square root of 5? No, it's a decimal. Square root of 2? No, it's a decimal. Can I jailbreak 5? Well, factor it. 5 and 1, 2 and 1 can't jailbreak. So I'm ready to rationalize. This 2 needs a partner in the numerator. 5 root 10 over 4 times square root of 2, square root of 2, 2, or 5 root 10 on 8. 5 and 8 don't reduce. Square roots and non-square roots don't reduce. 93. Can't reduce for 2 reasons. 3 doesn't reduce 5, but non-square roots don't reduce with square roots. 5 is not a V8 moment, and 5 does not jailbreak. Therefore, we rationalize root 5, and I get negative 3 root 5 on square root of 5 times square root of 5, 5. And that's it. Number 95. Here's a problem. If I was to multiply the denominator by square root of 5, or use square root of 5 on square root of 5, I'd have to distribute the square root of 5 to this 4, creating a mess. The square root of 5 times this square root of 5 would be good. What I want to use here is conjugates in the denominator. So I'm going to multiply this denominator. You'll see what happens here. By negative 4 plus 4 root 5. So I have to multiply the top by the same because I have to make sure I'm multiplying by 1. So the numerator, I'm going to leave the numerator as is for right now. I expect good things to happen in the denominator, and maybe later I can cancel a factor. So I'm just going to go 2 times negative 4 plus 4 root 5. When I FOIL in the denominator, follow this one, I'm going to get a plus 16. I'm going to get my outsides a minus 16 root 5. Whoop, hang on. I'm sorry, conjugates. This should have been minus and minus. Sorry about that. I'm going to get a plus 16. I'm going to get a plus 16 root 5 and a minus 16 root 5. Those cancel. And I'm going to get a minus 16 times root 5 times root 5 times 5. So I get 2 times negative 4, that's minus, that's terrible, 4 root 5, all on, let's see, 16 minus 80, or 64. And I see I can reduce the 64 and 2, although I'm going to get some more reducing, I think. Negative 4 minus 4 root 5 all over 2 reduces 64 to 32. And I can divide top and bottom by 4. And I get negative 1 minus root 5 all on 8. Now, can you see how maybe I could have kept the numbers a little bit easier to deal with in the beginning? Had I noticed I could have reduced top and bottom both by 2 to begin with. Okay, apologize for that conjugate error. Let's take a look at 97. One more conjugate type problem. Can I reduce this 5 with this 5? This 5 is not a factor of the bottom. It's a factor of this term, but it's not a factor of that term, so I can't reduce by 5. So conjugate, let's get it right. 5 root 3 plus 2 root 5 and 5 root 3 plus 2 root 5. I don't know what's going to happen in the numerator that would be good, but the denominator, good stuff's going to happen. So 5 times 5 root 3 plus 2 root 5, the denominator is worth foiling. I get 25 root 3 times root 3, 3. 25 times 3, I get 75. Then I get, outside, follow it, plus 10 root 15s, insides, minus 10 root 15s, they cancel. And then I end up with a minus 2 times 2, 4, and a root 5 times root 5, 5, minus 4 times 5, minus 20. So I get 5 times 5 root 3 plus 2 root 5, all on 55. That's why I don't distribute this 5 through in the first place, because maybe it'll reduce later. This factor of 5 reduces this factor to 11. I get 5 root 3 plus 2 root 5 on 11. So hope that helps, and you should be equipped to handle the remainder of this worksheet.